This is lecture number 10, part A, part 1. This is the first part of a two-part lecture on interrupts. Obviously, it's fairly complicated, or it wouldn't require 2 lectures. Some of the other things have only required 1 lecture that were pretty complicated. So there's a lot going on. Interrupts are integrally woven throughout the whole fabric of the Arduino, and so that's why it requires so much consideration to adequately cover this subject of interrupts. So that's what we're going to be looking at, this subject of interrupts. Please don't interrupt me while I'm ignoring you, and don't interrupt while the voices in my head are speaking. The word interrupt has a lot of interesting connotations associated with it. Well, interrupts basically allow programs to respond to the events as they occur. They allow the program to ignore events until they occur. They can handle external events, for example, the universal asynchronous receiver transmitter, to determine whether it's ready for or with the next character. It can examine a signal change on some pin, or perhaps a number of edges that have arrived on some pin. It can handle, so those are external events. It can also handle internal events, such as power failure, arithmetic exception, like a divide by 0, a timer tick, or an analog to digital conversion complete. Many uses for interrupts. You can detect a pin change, for example, using rotary encoders or button presses or some other signals. Watchdog timer. So that is, if nothing happens after 8 seconds, interrupt me. Interrupt timers can be used for comparing or overflowing timers. We're going to look at those specifically more in detail next time. SPI data transfers, I2C data transfers, USART data transfers. So these are serial data transfers, and it's very common to use the interrupts in their implementations. We'll look at that more in detail when we cover the serial communications. Then A to D conversions, analog to digital, EEPROM ready for use, flash memory ready. So a number of uses for interrupts. That's what makes them so powerful. Well, there are a number of different kinds of interrupts. There are external interrupts. Now, these external interrupts are also, pin change interrupts are also external interrupts, but these interrupts are specific in that they are built in to the Arduino, and they can be used directly within the Arduino IDE. The pin change interrupts cannot be used directly in the Arduino IDE. And finally, there are internal interrupts that are either timer-based or hardware-based. So, for example, the communications, like serial communications or the analog to digital converter, when the conversion is done, all of those are internal interrupts. And in this part of the lecture, we're going to cover these first 2 parts, the external interrupts. We're going to look at the basics of the external interrupts, and then we're going to look at pin change interrupts. And when we come back next time, we'll look at the internal interrupts. So, external Arduino interrupts can be used within the Arduino IDE. There are only 2 of them available, but for many applications, that's plenty. They can be run using int0 or int1. Okay, so interrupt 0, interrupt 1. So again, those are built-in interrupt channels. They are located on digital pins 2 and 3. So if digital pins 2 and 3 are set up as input, then you can use int0 and int1 interrupts. you can name their interrupts arbitrarily. You can give it whatever name you want, and you're able to use all 4 possible modes of interrupts. You can do low, change, rising, and falling. So what these mean is that, for example, rising and falling, if you have a signal and it has a rising edge, that rising edge can be used to trigger an interrupt. Or, likewise, a falling edge could be used to trigger an interrupt. Finally, a change. If there's either rising or a falling, that will trigger an interrupt. There's also the low. And this is a little different in that as long as that signal is low, it will keep triggering the interrupt. The interrupt will keep happening. So in a sense, that could be kind of like a way of switching in something that's like a loop command. Okay, so that's the low. So it's a little bit different than these other guys. So those are all 4 modes, and these 2 interrupts are able to use all 4 of those modes, these 2 interrupts, int0 and int1. We can also use this in C directly, and we can do all this in assembly language. So we will actually these external interrupts are something that we will do in all branches of the Arduino. Okay, so again, using C in assembly language, we're able to use the 2 external or the 24 pin change interrupts. In this case, or in many cases, the interrupt service routine names are predefined. And so again, and the pin change interrupts can only work with change. They don't work with rising edge and falling edges. They only work with change. And again, all of these can work with timers, counters, the COM ports, etc. So here is an example program that can be used to create an interrupt setup for using both of the external interrupts that are defined. So we have this command, attach interrupt. Okay, so attach interrupts, and notice I have these 2 commands. One uses interrupt 0, the other uses interrupt 1. And I've defined these names, Dr. Zap, interrupt 0. Guess who Dr. Zap is? Let's pause spell backwards. Okay, Dr. Zap, interrupt routine 1, so 0 and 1. This one is going to be a change interrupt. This is going to be on interrupting on the rising edge. So what this name is, this is the name for the interrupt service routine that will be called when an interrupt occurs. Okay, interrupt service routine has to be of type void, and actually it can't receive an argument. But inside you can do stuff. Okay, so and similarly interrupt routine 1. So this is the basic interrupt placement. So you define the interrupts in your setup routine, and then you define these interrupt service routines. And again, all of this is independent of the loop command. So that's where the interrupts would be placed. So here's an example. Here's the blink program using interrupts. Okay, now the difference here is that every time there's a change in a pin, for example, in our case, we're going to be looking at okay, so here's the state. It's low. And so we're going to define pin mode on that pin as an output pin. So that's the LED. We're going to attach an interrupt called blink that's going to operate on change. So it's attached to interrupt 0. Interrupt 0, if you recall, is connected to digital pin 2. So when digital pin 2 changes, this interrupt service routine called blink will take place. So notice that this is a blink program, but it's not like our other blink program that just runs by itself, toggles itself on and off. Instead, this toggles on and off by an external signal. So when the signal interrupt 0, which is connected to pin 2, when pin 2 changes either high to low or low to high, this routine will be called. And then in the loop program, we just have this digital write. Okay, we have this, and it writes the value state. And so notice that whenever the interrupt occurs, it goes here and it changes the state. So the state toggles. Okay, so that's the blink according to interrupt service routine. So again, we have this function, in this case called blink, that is what's called our interrupt service routine. So in general, the interrupt sequence follows something like this. So in this particular case, I have this setup program with some instructions. So in here, I'm obviously going to define my interrupts. And then I have my interrupt service routines. Okay, and then I have my loop command. And here's just some other function that's going to take the integer variable, or var, and it's going to convert it to a float and multiply by pi and return that value. Okay, so supposedly that's going to be used in here. All right, so this is the basic way that a program would be set up. So it goes through void, and notice it doesn't run these routines until they're called by interrupts. It'll pass right on to void. And so when an interrupt 0 occurs, okay, so we're in here and we're in the loop and we're doing its stuff. It's going around looping. A interrupt 0 occurs. So then it goes over to this interrupt service routine. It does whatever it's supposed to do, and when it's done, then it returns. So it was in this instruction, or whatever was going on here, and it basically returns to the same place that it was before. So as you can see, because you're being interrupted, you need to make sure that certain things are taken care of, and in the Arduino IDE, those things are taken care of automatically for you. There are things like the status register that keeps track of important flags, that you return the original flags so that whatever goes on in your interrupt service routine doesn't mess up those flags. So stuff like that, basic stuff like that. So, but again, the Arduino IDE takes all of that into account when it runs the interrupt. So again, here's the basic format for the Arduino IDE interrupt. We have interrupts 0 and 1. We have some function that we've defined. We define it somewhere. Okay, and then we have the mode, the 4 possible types of interrupts. So that's the Arduino IDE. We have, so in this command, we have what's called attach interrupt. So we're going to attach an interrupt to that port, which is that pin, which is actually D2 or D3. We're going to attach an interrupt. So it's also possible to detach an interrupt. And again, you would detach either 0 or 1. Okay, so we can attach an interrupt, or we can detach the interrupt. And so detaching the interrupt means that it's no longer functioning. Okay. Then we have these two commands, interrupts and no interrupts. Interrupts, when we just execute this by itself, enables the interrupts. Okay, so if you want interrupts to happen, then generally speaking, you'll want to make sure that you run this command. That command will enable interrupts to happen. This command will prevent or disable interrupts from happening. So this will disable all interrupts except the reset. The reset is actually its own interrupt, and you cannot disable the reset interrupt. Okay, we've covered the basics of interrupts using the Arduino IDE. Now we're going to talk about how to do all of these things in an advanced way using C. So this is going to be very helpful for us, and we will continue using this when we also look at things from the assembly language perspective. So, interrupts in C. Now, associated with the interrupt sources, there are what are called interrupt vectors. Okay, interrupt vectors. Now, these interrupt vectors are basically the place in memory that the instruction, the first instruction associated with each interrupt is located. Okay, does that make sense? So here we have the addresses. So notice that we have address 0000 is basically the reset interrupt. Okay, and so we have an external, there are a number of things that can trigger that interrupt. We can have an external pin, we have a power on reset, we have a brown out reset, watchdog system reset. So a number of things can trigger that interrupt. Okay, but this is where it goes. So whenever this reset is pushed, it instantly goes to this address. Located at that address is a jump command where it jumps to begin the boot loading. So that's where that is. After that, we have other interrupts that come in. Okay, so other interrupts at the various addresses. Notice that each of the addresses are 2 apart. Okay, they're 2 apart because it's a 16-bit address. It's going to jump, or actually it's a jump to an address, and so that's what it takes 16 bits to do that instruction, and so that's what we have. And these are the various types of interrupt vectors we have to work with. So this is kind of their name. Okay, so for example, timer 2, compare match A, timer 2, compare match B, and so forth. PC interrupt 0, PC interrupt 1, PC interrupt 2, watchdog timer. Okay, so we have, here are int 0 and int 1. Okay, and so you can see how closely tied they are to the Arduino IDE. We also have these timers, again, timer 0 stuff. Okay, we have the SPI, USART. So notice that there are 3 associated with USART. Analog to digital converter, EEPROM, analog comparator, 2-wire interface, or I2C, and store program memory ready. So these are all of the interrupt vectors. They can be written alternately this way. In fact, this is the way that they can be used, and these are the names of their interrupt service routines. They have a fixed name. So notice that the reset is not among these. The reset is its own deal. And so we have 2 different names that we can use for each of these interrupts. We can define it as vector. For example, vector 1 corresponds to interrupt 0 vector, which again is external interrupt request 0. Vector 2 is equivalent to interrupt 1 vector, and so forth. And so you can see that we have all of these vectors, and notice that they're in red, which means that those are predefined names in the Arduino IDE. These are also predefined. So we can actually use either of these 2. We can use the vector name for the interrupt service routine, or we can use the descriptive name for the interrupt service routine name. Either can be used. I don't know why they give these, but anyway, there they are. So there's the first half of the interrupt vectors, and here's the second half. Okay, so all the way up to vector 25. Okay, so again, timers, counters, serial, analog to digital, all of these different sources of interrupts. So these are all internal interrupts. The interrupt service routine is often also referred to as the interrupt handler. And basically, because the interrupt is interrupting the Arduino program, the loop, it will generally be interrupting the loop program. Unless you have a really long setup program, it'll generally be interrupting the loop program. And in the loop program, you can set things up. For example, you could say C, the variable C is equal to A plus B. And if C is a global variable, in your interrupt service routine, you could change, for example, the variable C. And then when it returns back to the main loop program, you find that C is not equal to A plus B. And you may be expecting it to be equal to A plus B. And so you can run into some kinds of problems. And so you need to be careful when writing interrupt service routines that you don't accidentally mess up a variable that you're intending to use. So, and in general, the interrupt handler must be invisible to the program. So there may be some side effects. That is, you may set some flags, or you may set some variables. In general, it can change program timing. So, for example, in your loop programming, if you're using a certain number of milliseconds that you want to operate, when the program is in the interrupt service routine, certain things are not happening while that interrupt service routine is running, and so that may change certain things. And so often you can't rely on dead reckoning when using these. You also need to be careful not to stomp on program state, for example, registers. And you need to save and restore any registers used. In general, when you write an interrupt service routine, you want to keep it short and sweet. So as an interruption, it's just like if you're in a conversation with somebody and you get interrupted. It's okay to be interrupted, but you want to be able to get back to what you were doing. And so if your interrupt is too long, it's possible for another interrupt to come in and try to interrupt while you're being interrupted. Okay, so there are priorities to interrupts. So if two interrupts happen simultaneously, which is possible, okay, because everything is synchronous, it's on a clock cycle, you can't have two things that happen on the same clock cycle. If it was asynchronous, then it would be pretty much impossible for them to happen simultaneously. But in the event of synchronous, you can always have the possibility of two. If you have more than one interrupt defined, you can have the possibility of two happening simultaneously. So there is a bit in what's called the status register, SREG, the status register, that allows all interrupts to be disabled with that one bit. Okay, so that's the I bit in the status register. We'll come back and look at the status register more in detail later. But this allows all the interrupts to be disabled or enabled with one bit. So here, set interrupt, so that sets the bit. Clear interrupt clears the bit. So this corresponds to the interrupts, and this is like the no interrupts in the Arduino IDE. As far as interrupt priority, the interrupt priority is determined by the order in that table. So we have that list of tables with the reset and interrupt 0, interrupt 1, and so forth. That is the priority. So for example, if interrupt 1 and interrupt 2 come in at the same time, interrupt 0 and interrupt 1, interrupt 0 is the one that's going to be done first. Okay, so the lower the address, the higher the priority. So address 0 is the first, that's reset, so and so forth. Okay, as far as external interrupts, basically those monitor either changes or conditions on signals on the pins. And again, so what causes an interrupt can be configured by setting the control registers appropriately. Pulses on inputs must be slower than the I/O clock rate. So if you have a pin connected to something that pulses, that can put out a little blip really fast, faster than the clock, then you can miss that external interrupt. So if you have a little blip, it's got to be at least as long as one clock pulse, which is 16 megahertz or 60 something microseconds, something like that. So you have to have that. Again, int0 and int1, they have a range of event options. They're connected this way. Int0 is connected to port D pin 2. Int1 is connected to port D pin 3. And then you have PC interrupt 0 to 23, in which any of these can be a pin change interrupt. Okay, so whenever that pin toggles, you'll get an interrupt. And so PC int. So notice int 0 and int 1, those are predefined. Then we have PC int 0 to 23. It's not quite 0 to 23. Not quite 0 to 23. There's one missing, and I don't know why they have it missing, but it's number 15. PC int 15 is missing. So if you look down here, PC int 0 to 7, PC int 8 to 14, PC int 16 to 23. Notice that 15 is missing. And actually, PC int 14 is actually not in port C. PC int 14 is actually the reset. That's actually equivalent to the... So actually in here, you actually have PC int 8 to 13. So basically, these PC ints are connected to port B, these PC ints are connected to port C, and these PC ints are connected to port D. So those are the pin change interrupt connections. That's where they connect. Okay, so that's physically where they connect. Now, we're going to talk for a bit about int 0 and int 1, how to program those in C. And again, at that point, we need to look at their registers. Now we talk about the external interrupt int 0 and int 1. These are controlled by a number of different registers. The first one is the EICRA, External Interrupt Control Register A. All right, so you can guess that there are probably other things, other registers associated with this. Well, anyway, we have these 4 bits that are part of this register: ISC11, ISC10, ISC0100. Okay, and basically, these two bits are for int 0. These 2 bits are for int 1, and so those 2 bits, these are how these bits are defined. And so basically, we can see that these bits correspond to what's called the sense of the interrupt, which we called previously the mode of the interrupt. Okay, so we can have, again, the low, the change, the falling, or the rising. Okay, IRQ stands for interrupt request. Why they chose that acronym, I have no idea. But anyway, that's what they do. So depending on what we put in these bits determines what kind of interrupt mode we're going to be working with. So that's the EICRA. And again, these are predefined variables in the Arduino IDE. EIMSK, External Interrupt Mask Register. Again, we're working with int 0 and int 1. So that's these 2 guys. And this, by setting these bits, we enable these interrupts. Okay. External interrupt flag register. So again, interrupt 0, interrupt 1, we can enable or disable these flags. Okay, so flags are sometimes used within a program to see what's going on. So just give some information. And these are determined by the I bit in the status register, whether we have interrupt enabled or not. Okay, so the status register has these various bits, and we're not going to talk about all of them today. The main one we want to look at is the global interrupt enable, which is this guy right here. So in our status register, we have a number of different bits: half carry, sign bit, overflow flag, all this kind of stuff. So the I bit is the global interrupt enable bit. So that's what's actually set when we do SEI, And that's what's cleared when we do CBI. We affect those, or CLI, excuse me. So here are the enable or disable interrupts. And so again, in the Arduino IDE, we have the commands interrupts or no interrupts. In C, we have the command SEI and CLI to enable and disable interrupts. So the reset, again, the reset interrupt cannot be disabled. Okay, all other interrupts can be temporarily disabled by clearing that flag. The default on the Arduino is for that pin to be enabled. Okay, so that's the default. And that's, so unless we really do not want interrupts, that's where we would leave it. So why would we want to disable the interrupts? Well, it turns out that some code is time critical and should not be interrupted. So in that case, we don't want interrupts. Also, multi-byte commands may be affected. So in other words, if you have some commands require multiple bytes. So let's say you're like for example a division. It may take several bytes to process that. So we're moving the data from one place to another, and if we've moved one half of the data but we didn't move the other, you can get some weird things happening. So it may be helpful to work with certain commands to disable the interrupts before you do that. Also, it's very common to disable the interrupts when you're in an interrupt. Okay, that prevents your interrupt from being interrupted. Okay, by a higher priority interrupt. Okay, so that's important. Interrupt flags. Interrupt frequently asked questions. What is the interrupt priority? Well, more than one interrupt event could occur at or before the previous one is processed. An interrupt event might occur while interrupts are disabled. The priority order is the sequence in which the processor checks the interrupt events. The higher up the list, the higher the priority. Can interrupts occur while interrupts are disabled? The interrupt events can occur at any time. Most are remembered by setting an interrupt event flag inside the processor. If interrupts are disabled, then the interrupt will be handled as soon as they are enabled again in the priority order. So you can set it up so that even if you can do it two ways. If you have an interrupt going, you have an interrupt and you're processing that interrupt and another interrupt occurs, you can have it just like completely ignore that interrupt as if it never happened, or you can queue up. That is, you can put it in like a line. You can line them up. So if you get multiple interrupts occurring, you just stack them up one after the other, and as soon as it finishes processing this one, it moves on to the next one and so forth until it's done processing all the interrupts. Okay, so that way there is a method in that madness. So that's important. What are volatile variables? Okay, volatile variables are a kind of global variable. Variables shared between an interrupt service routine and a normal function should be declared volatile. Okay, so interrupt service routines are a little bit different in the way they store variables, and so it's helpful to declare these as volatile. Okay, such variables could change at any time. In particular, they could be changed in the middle of an interrupt, and so the compiler must reload the variable whenever it is referenced, rather than relying on a copy that it might have in a processor register. Okay, so this prevents using a corrupted value that was corrupted because of an interrupt. So those are some things. So it's very common to use volatile variables when you want to pass something into or out of an interrupt service routine. Can ISRs be interrupted? By default, no. But it's possible for them to be interrupted if you allow them to be interrupted. When an interrupt service routine is entered, generally speaking, interrupts are disabled. So that's the way it is in the Arduino IDE. But if you were to design your own, for example, in assembly language, you might not put that in. You might choose to not put that in. When an interrupt service routine exits, then the interrupts are enabled again. Again, that's in the Arduino IDE. So in the Arduino IDE, the compiler generates code inside the interrupt service routine to save the registers and the status flags. So again, that's part of this notion of the interrupt service routine being transparent to the program, the loop program. You can turn on interrupts inside an interrupt service routine if you absolutely must. You can still do that. So you can do SEI within your interrupt service routines. So there are some good things and not so good things to do in an interrupt service routine. One of the things not to do is do not use a delay. For example, the command delay 100. Do not use the delay. You want to keep your interrupt service routines short and sweet. You can get the time from a call to millis, but it won't increment. So don't attempt to delay by waiting for it to increase. Okay. Also, don't do serial prints. Don't do serial reading. Okay. All of those take time. And actually, serial prints and serial reading actually require the use of interrupts. So I need to keep that in mind. Turns out you've probably already been using interrupts. Many Arduino programs use them. For example, the millis and micros functions make use of the timer overflow feature of timer 0. The hardware serial library also uses serial interrupts in handling the serial data. So you've probably already been using interrupts without even realizing it. And that's how transparent they can be. We're going to now move on to the subject of pin change interrupts. So pin change interrupts are a little different than the external interrupts in that you only have the one mode, the change. There are special registers associated for the use of pin change interrupts. So we have these pin change interrupt control registers, PCIe 2, 1, and 0. We'll talk about what those are in just a minute. PC interrupt flag registers. Okay, so we have those registers that are used for PC pin. So PC interrupt, pin change interrupt. I'll use those kind of interchangeably. Pin change interrupt mask registers. So remember, pin change there are 0 to 23 pin change places. So notice here we have 0 to 7. That should just be 8. PC int 8. Through 14, 16 through 23. Notice that 15 is missing. Also, PC int 14 is actually the reset. So these are associated with we have these different masks. So PC mask 0, mask 1, and mask 2. Okay, so basically every interruptible pin has a mask associated with it. And so if we set that pin to be 1, we enable that interrupt. Or that's part of the enabling process for that interrupt. There's actually kind of like multiple layers of interrupting for pin change interrupts. They're a little more complicated, okay? It's not too bad. And then finally we have the MCU control register. The MCU control register basically defines a number of things. We've already seen the PUD, okay, the pull-up disable pin. But we also have these two, interrupt vector change enable, interrupt vector select. So we have these two guys that are also associated with interrupts. We're not going to use those very much. It turns out that's something you can do, and there are reasons to do it, but I won't go into that. But anyway, those registers are there too. Okay, so how do we set up a pin change interrupt? Well, here are some things that we need to do. Okay, so first we need to set the PC interrupt control register. We need to set the associated pin. Okay, so that is one enable that we need to do. Then the other enable is to set the mask. Okay, so we need to set the mask and the control register associated with pin. So this is actually associated with the PCInt number, and this is actually associated with the PCInt pin. Okay, so we need to keep those straight. It's kind of confused. So this is the desired port, N. M is the desired interrupt. And sometimes this is where you might use the MCUCR. We have these two pins, and this would be to move the interrupt vectors into flash memory. So sometimes it's desirable to move them to flash memory. So that's the extent of how much I want to cover this, but that is something that can be done. Okay, so here we have in summary what's going on. So pin, so PCInt number. So notice 0 through 23 basically is in here. PCIe number, PCMask number, and then PC number vect. Okay, so there's a lot of stuff going on here. What's going on here? Okay, let's try to look at the very basics of this. The bottom line is that there are only 3 interrupt vectors associated with the 23 PC interrupts. So when we saw that list of interrupts, okay, you had reset, you had int0, int1, and blah blah blah, watchdog timer, okay, all those different ones. If you notice, there were 3 PC ints. Okay, so they're not int0, they're not int1, but 3 PCInt. PCInt0, PCInt1, and PCInt2. Those are the only 3 PC interrupt vectors for the Arduino. Okay, so there are 3 interrupt vectors, but there are 23 PC possible interrupts. Okay, so basically what happens is that when any pin on a PCInt number changes, it evokes an interrupt. So what does that mean? Okay, so PC interrupt. Okay, so we have PCInt. So here's our PC interrupt vector: PCInt0, int1, and int2. When PCInt, so PCInt0 is connected with the digital pins D8 through D13. PCInt1 is associated with the analog pins 0 to 5, and PCInt2 is associated with digital pins 0 to 7. Okay, so if there are only 3 interrupts for these 23 pins, how can we know which interrupt was intended? When any pin on one of these guys changes, it evokes an interrupt. So in other words, if any of these 6 pins changes, and assuming they're set up to be interrupts, if any of these changes, it will call the interrupt PCInt1 vect subroutine. Okay, that's what's going to happen. So basically 6 pins would all trigger the same interrupt. Okay, PCInt1. These pins would trigger PCInt0 vect, and these pins would trigger PCInt2. Okay, so it's important to understand how we can know which interrupt was intended. So in order to know, we first have to understand how things are kind of set. So in order for any pin to serve as a PC interrupt, its PCInt number must be enabled. So here are the different PCInts: PCInt0, PCInt1, PCInt2. If that PCInt is not enabled, then none of these guys can serve as interrupts. Okay? So if that pin is not enabled, then none of those are interrupts. So they're automatically ignored as interrupts. Okay, so first of all, if, for example, I want to use analog pin 4, that corresponds to PCInt12, then I need to enable PCInt1. Okay, the PCInt1 vector. I need to enable that. Then I need to set the mask bit associated with PCInt12. it must also be set to be a digital input. If it was set to be an analog input, if it was set to be an analog output or an output, then it has to be set. It will not serve, if it's set to be an output, it will not serve as an interrupt. Okay, so now let's suppose we have in PCInt1, we have, let's say, 2 or 3 of those pins. So let's suppose we have this whole port enabled. So notice that's port C. These are all the things in port D, and these are all in port B. Okay, so that's why the 0, the 1, and the 2. It seemed kind of out of order the other way. In other words, these digital ones are not in order with these guys. Okay, but that's because B is considered port int PCInt 0, C is PCInt 1, and D is PCInt 2. Okay, so suppose we have 2 pins in PCInt 1 that we want to use as interrupts. Okay, so assuming now that we've enabled this whole bank of them, when an interrupt occurs, at least one bit in that port, so when an interrupt occurs and calls the vector PCInt1 underscore vect, that interrupt service routine, that means at least one bit among these has been established, first of all, as a PC interrupt. So one of the bits that that has been established as a PC interrupt. So let's suppose that 9 and 12 have been set up to be PC interrupts. When an interrupt in PCInt1 occurs, that means we know that at least one of these guys has been interrupted. You could have multiple interrupted, but at least one of them is. So if you keep track of the bits in that port, then you can see which one has changed. Okay, so in order to keep track of the bits in that port, this requires volatile variables. Okay, so if, for example, this is associated with register C, we look at register C. Okay, and we have the let's say we know what was in register C. Then an interrupt occurs, which means one of the pins in register C changed. When we get into the interrupt service routine, we compare the new value of what was in register C with what was originally in register C. We compare them. Okay, and if any bit has changed, or in particular, if the bit that we're concerned about, okay, if we're looking at, for example, the bit associated with 12, if that has changed, then we know that that interrupt has occurred. Okay, so the fact that PCInt1 vect has been called means that one of these guys has been triggered. Okay, and so now it is you have to work with it to keep track of which one worked. So in this particular case, here's an example code. We want to use analog 1 and analog 4 for pin change interrupts. So again, these are PCInt9 and PCInt12. These are affected by PCIe, interrupt enable 1, and PCMask1. Okay, so PCIe1 is a bit, PCMask1 is a byte. Okay, and so I'm going to define these variables as volatile, these byte variables, port C state. So these guys are in port C. I also want to keep track of what was happened in the past in port C, and then what bits changed in port C. So all of those are volatile. I'm also going to define this variable int called, and actually that should also be a volatile. That should also be a volatile variable. Int called. So, or this is just my way of saying that an interrupt was called. here's my interrupt service routine. Notice that because these guys are in PCInt1, I use PCInt1vect as my interrupt service routine name. So I use ISR PCInt1vect, and this now sets up my interrupt service routine, and here's my interrupt service routine. Notice that I don't have to do a void interrupt service routine. That's kind of taken into account by the fact that I'm using this command this way. So now port C passed is equal to port C state. Okay, so in other words, I took sometime in the past, I captured what was in port C. And so since that's the case, I'm now putting it into this variable port C passed. Now port C state is what the current state of port C is, which I can obtain by using pin C. Okay, so I have the present, I have the past, and the present and the past, and now I'm going to compare them. So what I do here is I do an exclusive OR, and this allows me to check if they're the same, I'll get a 0. If they're different, I'll get a 1. That's what an exclusive OR does. If they're the same, either 1's 1 or 0's 0, I get so 1 1 or 0 0, I get 0. If I get 0 1 or 1 0, that is if they're different, that means a change has occurred, then I get a 1. So this changed bit now, by doing this exclusive OR, this changed bit is going to have a 1 in every place where there's a difference between these two ports. Okay. Now, what I'm really concerned about is, do I have a change in pin 9, PCInt 9 or PCInt 12? Okay, those are the ones I'm most concerned about. Okay, so let's see. So this is kind of a test program. So I'm first going to set the data direction register so that all of the bits in port C are all input bits. Then port C, I'm going to write to port C this number, which basically, for my purposes, puts in a pull-up resistor. Okay, so the default state here is a 1. Okay, and so I'm going to do a pull-up resistor here. Port state. So now I'm going to read in the port state. So this is in my setup routine. So this is the first thing that actually runs in my program, and so I'm going to first load into port state C whatever happens in pin C. Okay, so I actually have a grasp of what's in pin C. And now I'm going to use a serial port to write things to the console. And then I'm going to set up my pin change interrupt control register, and I'm going to let PCIe 1. So notice PCIe 1 is the port, which is actually port C, and it enables that port to use pin change interrupts. Okay, so that's what this command is doing. It enables port C to do pin change interrupts, but it enables the entire port to do pin change interrupts. Then I do the mask, and this mask allows, so this command sets up pin 12, and so it makes that equal to 1, and this sets the bit for pin 9, or PCInt 9, which is the same as, so PCInt 9 is the same as A1, PCInt 12 is the same as A4. It's those pins. Okay, so now I have set up pins A4 and A1 to be pin change interrupts. I had to do all of this stuff in order to make that happen. So that's what happens in my setup routine. In my loop routine, notice the way I do this loop, I'm actually going to clear the interrupt. That is, I'm going to disable the interrupts, then I'm going to reset the interrupts. Okay, so while all this stuff is happening, I'm going to disable the interrupts. So if I'm interrupted while while it's going through and doing this stuff, then I'm interrupted, then it, if an interrupt occurs, it's ignored. So if int called, int called means that the interrupt service routine was called. Something triggered a call to the interrupt service routine. That can only happen if A4 or A1 changes state from 0 to 1 or 1 to 0. Okay, so if that's the case, then I have this loop going on here. The first thing I do is I set int call to be false, so that I don't accidentally just keep doing this loop here. So then I check to see, is bit associated with A4, has that changed? So changed bits ORed with this number gives a 1 if that number is, I need to do an AND, don't I? That needs to be an AND. If change bits and this is equal to 1, then A4 is interrupted. Otherwise, if changed bits, then I'll print A4 interrupted. Yeah, that needs to be an AND, not an OR. Similarly, this needs to be an AND, not an OR. So basically, this is looking at pin 1 to see if it has changed. If it has changed, then A1 is interrupted. Okay, so basically all this is doing is sitting here, and as the interrupts come in, the basic idea is as an interrupt comes in, as an interrupt comes in, if A4 has been interrupted, it should print that. If A1 has been interrupted, it should print that. Otherwise, it doesn't really do anything else. So it's just really, the intent here is just to kind of test these interrupt service routines, and so this would do it. Okay, so notice how simple this interrupt service routine is. We're just doing the bare minimum that's needed to work with in all of this. So this is just an example pin change interrupt. Okay, it turns out that pin change interrupts are confusing enough for most people that they've actually created pinchangeint library, and you can find it at this site. It's a library that does the bookkeeping for you. It simplifies the process, but in the process also hides some important features. So this is the calling for the pin change interrupt. Okay, so you give the interrupt number, and that's in 0 to 23. You give it a function name, and so again, you can use any function name that you want, and then mode. Okay, and so here is an example of a pin change interrupt using that library. So we're going to include the library here, so it requires both of these to do it. I'm going to set up a name, pin B. Notice pin B also has the port B name, but so I'm going to redefine that name to be pin 17. That's the one I'm going to use. And for the EduShield, that's actually pin B of the encoder pins. Okay, so I can use this with the EduShield to test this program to see how it works. Okay, so we go through and we set up P to be pin mode, and then we do an attach interrupt. So we're going to use pin B here. Pin B is, again, interrupt number 17. We're going to use the file name blip count. So here's blip count. Okay, here's our function blip count, and we're going to use a pin change. Okay, so this is an example of using the pin change interrupt library to do pin change interrupts. And the library is nice, but as you saw, it's really not that much more complicated to just keep track of the state of port C before and after. Okay, just like in the previous example. So this is actually not much simpler, really. But for some people and their understanding of things, especially when we look at this program here, we see that we have to do a number of things. We have to set these registers and stuff like that. And for people who are not familiar with or comfortable with setting registers and working with ports, this can be a little unnerving. So that's why a library like that exists. So we've talked now about the major details of working with external interrupts. So whether they're the predefined int0 and int1 or the pin change interrupts 0 to 23, we have a number of options for triggering a process from outside to our Arduino. So if you can use int0 and int1, that's probably the easiest way to go. But it's not always possible. In other words, your shield might require the use of those particular pins for some reason, and so you don't have access to them. So what the Arduino allows you to do is it allows you to access any pin as a pin change interrupt. So we have a lot of capabilities. So this is the first part of our two-part discussion on interrupts. When we come back next time, we're going to talk about how to use timers and other hardware to work with interrupts. Thanks for watching.